Hello, I'm Tamesh Shukla. This is Lab 3 of the Circuits Lab for Physics 2012 at Georgia Tech. The aim or purpose of this lab was to apply the principles of energy conservation or loop rule and steady state current to predict the behavior of series circuits and to utilize actual electrical equipment like multimeters to measure differences in current/potential current and voltage in circuits, and was also to examine how resistors and capacitors behave. The formulas used was Kirchhoff's loop rule, which says that the sum of voltages gained or lost in a closed loop sums always to zero. The classic capacitor equation, which is C is equals to Q over delta V, where Q is charge and V is voltage and C is capacitance. The capacitor discharge equation, where the change in voltage equals to the initial change in voltage times E, the exponential factor, raised to the power of negative T over RC, where T is a time constant, R is a resistance, and C is capacitance, and of course Ohm's law, which is just V is equals to IR, voltage equals to current times resistance. The first experiment we did was a simple series circuit where we had the circuit as you can see here. We had two batteries, each of 1.5 volts. We had two ammeters, and we had two resistors, 47 ohms and 100 ohms. So if just by simple Ohm's law, the predicted current would just be 2 times 1.5, which is 3 V over R, and R is 100 plus 47 or 147 ohms, and that comes out to approximately 0.02 amperes. And the recorded currents we got when we actually did the experiment in lab was 19.6 and 19.5, which is really close to 0.02. If you replace the ammeter with a voltmeter, the voltmeter would read plus 3 volts, but the ammeter would read 0 milliamperes, right? And that's just because the voltmeter creates a short essentially. And if you connected the voltmeter across different, if across the 447 ohms and across the 100 ohms, you would get 0.094 of from the 47 ohms and 2 over the 100 ohms. And if you do Kirchhoff's loop rule, this is plus 3 minus 0.094 minus 2, which just sums back to 0 when you come back. Hence, loop rule is actually satisfied. This is the graph of the change in voltage. As you can see, it goes up 1.5, goes up another 1.5 because of the two batteries, and the resistor eats up 0.094 volts, and that second resistor eats up 2 volts. When voltmeters in parallel, current flows to the path of least resistance because they are practically infinite resistance. So circuit is unaffected, so ammeter won't change. But when voltmeter disconnected across 100 ohm resistor, again the voltmeter connected because it would eat some current up, so the ammeter current would ammeter reading would decrease. Uh, yeah, but if the ammeter was in parallel with the 100 ohm resistor, the current would be decreased slightly in the other ammeter, if that makes sense. Yeah, this is the same graph that was in the previous slide as well. The second experiment we did was a simple RC circuit where we had two light bulbs of 10 ohms and 20 ohms with one farad capacitors and the same two 1.5 volts batteries. So we first charged the capacitor using the two batteries, and then we would discharge the batteries and then the capacitor run its current over the two light bulbs, and the light bulbs would start bright and then dim over time, which suggests the capacitor discharging. Is the calculated time we took was a 10 ohm bulb took 49 seconds to dim, and a 20 ohm bulb took 68 seconds to dim, and that just fits with the the capacitor discharge equation because more resistance, it would the difference in voltage would be more, hence more time to dim essentially. It would take more time to dim. This is a video of the RC circuit. This is a short one. You see it discharging over time, and to completely dim it would take approximately, this was a 10 ohm, so I believe 49 seconds. So for the what if question, what if we charge a capacitor with no resistor in the circuit? So if that was the case, the capacitor will reach charge immediately. So in theory, the capacitor will reach charge immediately, but in reality, there will always be some sort of resistance in the circuit. So V is equals to IR. So yeah. Also, like real circuit components cannot supply infinite current. So capacitor will charge very fast but not instantaneously, and the ammeter will reach super high current and quickly drop to zero. Sources of error. So internal resistance of the batteries affecting total circuit voltage, resistance of connecting wires slightly altering measured values, ammeter and voltmeter altering the circuit when connected, multimeter calibration or scale reading errors. There could be inaccurate or fluctuating contact points in the circuit, resistor tolerances causing actual resistance to differ from labeled values, human error in reading or recording current and voltage measurements, or incomplete discharge of the capacitor before timing the RC circuit. those are the sources of errors that you could encounter while doing this lab. Anyways, that's all from me. Thank you so much, and it's Tamesh Shukla signing off.